Do it.
We'll start in a couple of minutes, those joining later. And just to remind people, this is for you, so don't be afraid to chime in and say, Phil, you're full of plasma or whatever you want to call it. And please do ask to clarify. And if you want to discuss something, that's fine. There's no fixed agenda. This is just we'll plow through the same material I have, and I'll try to shed light on what I think is important to know about using spectroscopy. Morning. It's Thomas. Wow. Nice to see you. All I need is Andy School, and then I'm probably scared to death. Okay.
Are we starting, or did we miss something?
No, we start at 5 past.
Okay.
There was a tradition at Christchurch in Oxford when I was singing in the cathedral choir there that the service was at 6, but it started at 5 past because that was the longitude in time. that was the excuse anyway.
Well, Momo is my hero because it's impossible to get in this building.
Oh yeah, I know.
Yeah.
I couldn't get in last week. I forgot my wallet.
Come find me and you don't answer your phone.
Oh, I don't. My phone is off because I'm in it. So, okay. All right. So it's 10:05. We'll start up. Last week, I basically introduced some business about plasmas and the atomic spectroscopy, or the spectroscopy that we use to look around us in the universe. How that is a tool to understand the plasmas, and while we can build plasmas in the lab and we can build them in the computer, when it comes to observations, we have to go from, you can imagine doing the calculation where you build yourself a plasma, you set a temperature, density, you set distribution, whatever you like, abundances and all that, and then you add in some atoms, and then you get the radiation that comes out. And what this is all about is trying to understand how that radiation can tell us, going backwards from the observations through the atomic calculations that need to be done in order to tell us about what these plasmas are doing. And we got about this far last time. So I'm going to proceed with let's see, yes, by telling you a bit more quantitatively about what atoms sitting inside plasmas are. We learned that plasmas, and we'll see some properties of them that are typical. Let's just expand this. There we go. So typically atoms, if you were to take one atom in the universe and it has a charge Z in the nucleus, and one electron around it, then the size of the atom is given by about 0.1 nanometers, about 10 to the minus 10 meters, which is 1 Bohr radius. Okay. Now, if we then put that radius atom into a plasma that has a particle density of n per cubic centimeter, then we have an average spacing between them. And so if you had a large number, say Avogadro's number per cubic centimeter, then the atoms would be packed fully together. And that's no coincidence, of course, because what that defines is that atoms are touching each other very closely in a solid or a liquid state. And in that case, we know from our elementary physics that the atoms are very strongly perturbed, such that any radiation you scatter off this thing or is emitted by this thing is going to have lose some of its identity that it had as an isolated atom, and it's going to give you something called band structure, and that's what semiconductors work and all this stuff. So the physics, we know this stuff. So, but if we now go to a very high temperature and a lower density, typical of many plasmas, then the matter is in a plasma state, and what that means something very specific in terms of a plasma number. We have very strongly, because it's hot, thermally fluctuating microfields, we have sharp atomic levels sitting inside what is now a much more diffuse thing, and it can be treated perturbatively, and this is typically how we treat plasmas in from the solar interior all the way up out into things like planetary nebulae, low density plasmas in the stellar medium. Now, one of the properties of a plasma is the electrons are incredibly mobile, being very lightweight. And so in those conditions, macroscopic electric fields are quickly shorted out. That doesn't mean that E is zero. In fact, E is never zero in the neighborhood of an atom. But what it does mean is on macroscopic scales, if there's an imbalance somewhere in a plasma between the charge densities, those will quickly be shorted out by the motion of electrons. That could be associated with collisions and heating, all kinds of things, but we won't worry about that for the time being. But we mentioned last week, macroscopic magnetic fields are pervasive. I mean, there are no free magnetic charges, and so what one has is the potential for magnetism to, it doesn't know anything about there being a plasma there, it just sits there and and the plasma will interact with it, but we can have macroscopic, and we do have macroscopic magnetic fields, as is evident in things like tokamaks, and all the way out to things like, clusters of galaxies. And most astrophysical plasmas are, in fact, in this sense, magnetized. Okay. When you embed an atom inside a plasma, and you remove electrons from it because you've put enough heat energy per cubic centimeter to raise the temperature enough to knock electrons off so that it reaches some kind of equilibrium or quasi-equilibrium state, then you've got a system in which, very unlike the air around us, you've got particles that interact with a cross-section that goes as 1 over the energy squared. What this means is that if you happen by some process to generate a high energy particle in there, it's not going to interact very much with the ambient particles. But for the bulk of particles in astrophysical plasmas, we're going to end up working with something like the Boltzmann distribution or small deviations from it. And one of the nicest resources I personally enjoyed learning from is Braginski's 1965 paper, the first issue of a review in plasma physics. It's incredibly clear. Yeah.
Ask a question. So why does the cross-section decreases with increasing energy? Like, because when you're walking in the rain, right, and you're walking faster, there's more rain coming on you.
Right. It's because there's a 1 over R potential. It's the same for gravity. And you just have to go through and do a classical collision between two charges and then evaluate the amount of energy exchange and the probability of that making that kind of transition.
Okay.
Okay. And so this is something that should be remembered. So those numbers, those equations.
I think it's because it doesn't spend much time in the potential well.
I see.
It moves through it very fast.
Yeah. Right. Yeah. And then if you evaluate, say, 10 to the 4 Kelvin, the electron's moving at 400 kilometers a second, and the atom is 10 to the minus 10 meters. So there's an instantaneous blip that the atoms feel. So you can roughly compute this thing, the things called collision times, when you don't have too big a deviation from a Boltzmann distribution, but a little bit. So this is the Chapman, Cowling, Braginski, Bogle-Lyubov, these kind of low perturbation methods that are outlined particularly clearly in Brzezinski, you end up with a collision time between particles, and those are given by these formulae here. Now, these are given with the temperature in electron volts. So 1 eV is about 11,000 Kelvin. So for 11,000 Kelvin, the electron collision time in a plasma that has a density of, say, 10 to the 11 particles per cubic centimeter, the top one would give you a time scale of about 10 to the minus 7 seconds. So that's the top of the solar chromosphere, right? Now, in the corona, the electron volts are a factor of 100 larger, the energies, and that gives you a much larger time scale of some fraction of a second, and the density is lower as well. Now, the ions are that much larger time scales because they're slower, and they interact mostly with exchange energy with the other ions, not much with the electrons, and that collision time can be on the order of, say, a minute almost in something like the solar corona. Okay. So what are those timescales? If I were to let a test particle loose with roughly the same energy as all the others in the corona, say from a piece of heating, it would relax on those timescales to form part of the plasma with that kind of property there. Now, the other thing we mentioned was the presence of the magnetic field. And so we have also what is, of course, the gyro frequency, again, the classical motion, helical motion. And those frequencies are given by Brzezinski here in terms of, measurements in Gauss. So, for instance, a 1 Gauss field is going to have a plasma frequency of electrons of around 10 to the 7. So that's 10 megahertz. So what's going on is that when you compute the product of the omega, the gyro frequency, and the temperature, that is a measure of the number of times the field line goes around between collisions. Okay, so if that omega tau is very much bigger than 1, and this is a good number to remember, that means that the between collisions, all the ions and if the electrons satisfy that as well, they're all going round and round and round. They follow the trajectory of the field lines roughly. I mean, there are gradient things and moments conserved and all this stuff, but in terms of a first order effect, the ions and electrons move along the field lines, which is why we see things like coronal loops. Okay, so and that's called magnetized. The ions become demagnetized in the solar photosphere, roughly. So what that means is that the collisions occur before it makes a complete gyration. So that if it happens a lot of collisions between one gyration, that means the magnetic field is dynamically not important for the kinetics of that. So that's the opposite regime. Okay, right. So we have a thing called the plasma parameter, which defines if there is such a thing as a plasma at all. And by that, what we mean is the plasma parameter. Let's imagine having a cube, a sphere of volume 4 pi times what I've got written here is the Debye length. So this is the distance out to which individual electrons see each other as being charged. Now, if we go further away than that, they become neutral. Okay. So this is telling us if this number is 1 omega, then we have a lot of electrons inside, all strongly interacting with each other by electrical charges. But if that number is very small, we have such a tenuous plasma that those kind of collective effects don't count. And here are some plasma parameters, and most of the plasmas I'm going to be talking about will be on the right-hand side. So we're going to have hot and diffuse plasmas. We're going to have ionosphere, fusion devices, space plasmas, etc., etc. Okay. Here is a vast number of orders of magnitude on the y-axis. That's 10 to the minus 3 to 10 to the 27 or something. So 30 orders of magnitude on one axis. Okay. So, but it shows you where we are in the temperature on the x-axis and density on the y-axis. Now, we're assuming the plasma has relaxed, so we can define such a thing as a temperature and a density. Okay. But this roughly shows you what you can pick your favorite plasma. I mean, you know, you can certainly have at very low temperatures things called metals, and that's because they're cool. They have almost free electrons like copper. They float around, but the ions are fixed. Not enough thermal energy to loosen them up. And then all the way down to very hot, tenuous plasmas associated with like clusters of galaxies and stuff on the bottom right-hand side. And in between, we have things like corona, magnetosphere, ionosphere, interplanetary, solar wind, interstellar, you name it. And right there in the middle of this figure, the chromosphere and solar corona. This is why the sun is so important in understanding plasmas in general. And remember, that's our goal with the spectroscopy, is to understand the plasmas. That could include the magnetic fields in the plasmas as well, of course. So those things are very important because, and also the magnetosphere, ionosphere, you know, we can measure these things in much greater detail than any other kind of plasma that we have. That might include the ionosphere of Jupiter or magnetosphere of Jupiter as well, right? Because we have probes that can go and do that. But what I'm trying to say is that in terms of, you know, a Rosetta Stone for understanding plasmas in astrophysics and plasmas in general, these are very good places to start. The only disadvantage is that we can't go in and measure temperature and pressure with a thermometer and a barometer. So we've got to do something with the radiation coming out of it, unless you happen to be sitting on the Parker Solar Probe, you know, with your fork toasting muffins and outside of the shade. Okay. So we know that actually plasma is not a very big component these days, apparently. The current paradigm is that the dynamics on large and small scales insists that we have both dark energy and dark matter. So on the scale of a galaxy, we must have dark matter to explain rotation curves. On the scale of the universe, we have to have dark energy to explain the expansion. And of course, atoms, this is just from a few years ago, some estimate, these change. Now, I don't know if that paradigm survives. I mean, by the time you end up putting epicycles and epicycles like dark this and dark that, you know, just philosophically, you have to question whether you've actually got the right picture of the universe at all. Okay.
So Roger doesn't believe in it.
Roger
Penrose.
Penrose, yeah. Yeah.
Also recent observations with James Webb kind of put some question marks in there.
Yeah, so there are brief discussion here about the fact that there are people that don't agree with that, and there are some interesting things coming from things like the James Webb at this point. Okay, so in terms of the universe, plasma is kind of stuck in the middle. I mean, there are clearly gases and solids and liquids because we're sitting in them. But if you look at this and you go from the bottom up, you see that what we're familiar with is actually unrepresentative of the entire universe.
Real quick, so atoms is everything that isn't dark matter or dark energy?
Yep,
Okay.
right. Baryonic mass,
Okay.
the atoms and electrons and all that stuff. Okay, so why is plasma so important then? Well, because these other things are dark, it's the only thing we can use to observe the universe. The only other thing is gravitational waves that I'm aware of, and maybe some neutrinos and things like this, but you know, those are dominated by the sun. So plasma gains importance here because it radiates a lot when it's hot. I mean, the energy, it's a lossy system. And how does it lose energy? Well, it can do it by mass motions, it can do it by conduction, it can do it by a whole bunch of other things. But in things like the sun loses energy by radiation, and it loses a lot more energy through radiation than it does by the solar wind. I mean, the actual mass loss rate of the sun is determined by the radiation, not by the loss due to the solar wind. Of course, the solar wind determines the rotation rate because photons don't carry angular momentum except for the spin that they have along the direction they're traveling. Okay, so the plasmas then are very important in spite of the fact that they're not very abundant. So let's have a quick look at some plasmas here. And we have terrestrial plasmas on the left, and I won't go through this. I'm just going to show you that there are real plasmas with real numbers associated with them that we think we know about. And so, you know, interesting things like lifetimes, you know, even on the sun, we can see things change on a time scale of a few seconds macroscopically, which is really remarkable. I mean, it's hard to do that. And in things like solar flares, we have to appeal to special conditions that lead to things like what we call reconnection, of course, that can do this kind of thing. But then there are, you know, evolution of things on time scales larger than the age of the universe. Okay, so anyway, this is just an example. The difference between, you know, plasmas and what we're breathing here is, of course, that you know, the temperatures are very high. Last week I mentioned why the temperatures are so high. Well, gravitational collapse. There's only one direction in gravity. And as the universe started apparently from something, and then it expanded, condensed out, and then started collapsing, it dragged with it the magnetic fields we just talked about, because there was just enough energy and charges to pull those things around. Actually, the origin of magnetism in the universe is still a subject for research. It's kind of interesting to know where the primordial magnetism came from. So anyway, we have, unlike air, we must pretty much consider that we're going to have non-Maxwellian collisions. Air has cross sections that don't really depend on energy. I mean, if you go to extremely high energies, then you start ripping electrons and ions off and neutrinos. We're not talking about that. Just at our air temperature, you know, it's just billiard balls rattling around as far as we're concerned. It's just very light and floating around with a certain temperature because the sun has heated up our atmosphere. On the other hand, in the plasmas, you think about something like the corona or the ionosphere. You know, the ionosphere exists because of radiation that's EUV sufficient to drive electrons off of atoms and molecules in the upper Earth's atmosphere. So immediately, you know, that's a non-equilibrium process. So why should they form a Maxwellian distribution? Only if, once formed, the collision times are shorter than the changing state of the radiation. So you know, we must not expect Maxwellian distributions, which is really, really bad news, because we go from a non-relativistic three-dimensional space plus time to a six-dimensional space and time, because we have a Boltzmann equation instead of fluid equations, for instance. Okay, and then we have to worry about collective effects. These are, think of wave-particle interactions. So you have some kind of imbalance in the electron charge distribution that wants to relax to trying to get to a Maxwellian, and before it can share all its energy, one might have, for instance, a electrostatic wave. You certainly have magnetic waves, all this stuff. Electrostatics tend to be very high frequencies. We won't talk about that very much, but typically what we have here, these are the kind of things that we should expect to impact the radiation from spectroscopy that we're using to try and understand this. Okay, so why do we want to do spectroscopy? Here is the famous Auguste Comte, a logical positivist. And he basically, at the time that Fraunhofer had developed the spectroscope, and people like Bunsen and Kirchhoff were working on laboratory spectra, and you know, Bunsen's invention was different from what Newton used, being 2 centuries later, or a century later and a half later, namely in the fact that it could resolve things much better. So Newton was looking at just a broad spectrum of things like sunlight, whereas these guys suddenly could split things up. And as we look back from a post-quantum mechanics era that we're in, it's quite easy to see that suddenly all this smooth stuff is actually consisting of a bunch of things. In fact, that's why we have things called Fraunhofer's lines. So this guy didn't believe that you could actually learn anything unless you physically touched it or you physically measured it. This is sort of logical positivism, whereas this is action at a distance we're looking at for Fraunhofer. And his discovery was, like I said, you have this colorful continuous spectrum there. But you notice these unchanging lines from the sun, and he labeled them from A through K, and we still use these nomenclatures today. Right smack in the middle of our eye is developed to be sensitive to these things. No coincidence again. The sun's been around 4.5 billion years, and it's roughly the same spectral type, so it emits the same kind of spectrum. So our eyes are a very crude spectroscope: red, blue, and green, etc. Mine are more black and white than that, actually, but never mind that. But Fraunhofer actually saw that these things were there, and then people like Bunsen and Kirchhoff noticed the same lines in the laboratory spectra. So you have a Bunsen burner, you throw a bit of sodium in it, and hey presto, those lines at D show up, but they don't look black in comparison with the bright background of the sun. They look bright. So we won't worry about types of spectra. This was just taken from Wikipedia, I think, but just for the sake of interest, notice that Comte was writing about the same time that these guys are doing this work, right? Which is kind of unfortunate. I mean, this poor guy Comte really sort of got it in the neck as a result of this. Now, quantitatively, then we go from a spectrum with a lot of lines on it, which are not shown here. Here is the continuum. And so Comte says you can't possibly do this, right? You can't just look at the sun with a continuum brightness and say, as a function of wavelength, whatever the material is that's heating it, whether it's, pineapples, like Tom Ayers likes to say, or whether it's rocks or whatever it is that's in the clouds, water, whatever it is that's emitting in the sun at the moment, we don't really know just yet. But you can just take with the invention of quantum mechanics and saying, well, if it's like a coal fire, if it radiates radiation that's roughly in equilibrium, we know it can't possibly be equilibrium because the sun is radiating in only one direction. Therefore, explicitly, it's not in thermal equilibrium. But say there's some processes in there that maintain the temperature of the gas and the plasma particles in it at one temperature. What would be the temperature as a function of wavelength of the measurement of the absolute brightness corresponding to a black body? Hey presto. Now, of course, this couldn't be done at the time of, we needed to understand black body radiation. So this was a little bit later. But here we see that immediately we've got a number on the left-hand side, which is not too far off what is actually a modern kind of understanding of what the surface temperature of the sun, as measured by the width of the distribution function of the atoms in the surface of the sun. This is about right. And so this is another power of the spectroscopy. Last week I gave the example of a laboratory and solar spectrum where you saw the broadening of the lines due to the pressure, and that really high pressure in the lab plasmas. This is another example. In that case, we were talking about a spectrum reflecting the pressure. This one is now reflecting the temperature. So we now believe that we're in business here, and the modern success of astrophysics, and in particular stellar nucleosynthesis and evolution, is so overwhelmingly sort of making sense to us that you have to say, we've really embarked on something interesting here. So spectroscopy is sort of the right way to do it. Now, the sun, if we look at more detail, and now I'm looking at shorter wavelengths, these become of interest because they tend to be capable, owing to Einstein's photoelectric effect, of having a photon with an energy that's sufficient to do some damage to things like the air around us. So what I'm talking about here, this is ultraviolet. This is beneath the wavelength of what we can see. And so what you see is, from the top right, you see the continuum sort of dropping like the Planck function, okay? And you see these lines superimposed on it, just like Fraunhofer did, and we'll get into why those are absorption lines soon. But now, as the continuum drops off, because there's not much heat not enough heat in the surface layers from where that radiation is emerging, that's going to continue exponentially to drop off. That's log intensity on the left-hand side, sufficiently that we suddenly start seeing some funny stuff. And this funny stuff is the emission lines of various elements that we now know to exist. And these, the formation of these lines is quite a lot simpler. So if you imagine an absorption feature occurs because you have like a bright headlight coming towards you, and if you were to put some sodium atoms in between you and that bright headlight as it's moving past, you would see a nick in the spectrum where the sodium took the light out. But now if we take away that bright light and just look in the darkness, well, we'll see sodium in emission. And as we go to shorter and shorter wavelengths, that's equivalent to just turning down the temperature of the bright light. And suddenly we see these emission lines. So this is not at all surprising. I mean, this is a natural thing that happens if once you accept that the sun is dropping like a rock exponentially, that you find some junk lying around that might be a hotter temperature. The question is, how does it get that hot? And that question, you know, is the heating mechanism. Okay.
Now I have a question for you.
Yeah.
Last lecture, you showed that the Boulder series went out to n equals 30,
Yeah.
and the Lyman series here seems to go out to n equals.
Yeah, it's going to go out to less than that, probably.
Why is that? Right, there doesn't
It
seem.
may actually go out to about the same. Remember that Lyman beta has the same upper level as Balmer alpha.
Okay.
Lyman gamma has the same as Balmer beta, et cetera, et cetera. So those are related, and depending on the resolution of the spectrograph, you will see these series of lines that approach a continuum level, but the lines will blend into each other before they reach that continuum level, owing to the motions, the Doppler shifts of the lines. It's a plasma, so it's hot, and owing to pressure broadening. So what that means is that what was a sharp line is becoming less sharp because its lifetime is reduced as a result of the collisions. And as you go to higher and higher n, the atoms get bigger and bigger and bigger, and so they get more and more collisions.
Right, so why doesn't that happen to the Balmer series?
It does. I think they should behave in relatively similar ways.
All right, I was just looking for more Lymans here.
Well, this is a low resolution spectrum as well. Yeah.
Okay.
No, but it's a very valid question. If we go to incredibly low density plasmas, well, you know, I'm presuming now that we have knowledge from the 21st century that that's the sun. This is a planetary nebula. We know what a planetary nebula is. It's an old sun that's puffed out, and what was dense is now tenuous. And we see various things in here which have been identified. A totally different, this is visible wavelength, right? A totally different kind of spectrum from the sun. And what it is there's a little white dwarf at the middle of this beautiful nebula that's irradiating the tenuous material with photons in the UV region. And it creates the plasma because this is expanded so much, it's a very, very low density. And the energy balance turns out to be, well, you can see we've got neutral magnesium, neutral H beta, neutral oxygen, oxygen with 2 electrons removed. It's going to be 10 to 20,000 Kelvin just from seeing that. I hope you can understand why that is at the end of this whole thing. But what we see there is the presence of things with 2 brackets around it. And those 2 brackets mean to spectroscopists, this would never show up in a lab spectrum. It's because the density is so high that the levels involved in emitting that transition would be collisionally de-excited before it can radiate. So immediately we know this is a very low density object just by looking at this spectrum. So we're looking at it from the 21st century, but of course the development of spectroscopy throughout the 20th century is what led to this kind of discovery. So really, if we look at the achievements of astrophysics in the early part of the 20th century, we have some remarkable achievements, which I mentioned earlier. And this is just 1926. Eddington was a bit of a miserable guy that tended to challenge it, most people that he could. But this is sort of the way science was done by these people in those days. Basically, the work and the examples of the spectroscopy were the tools used in order for them to build an edifice based upon quantum mechanics and relativity that we now is our current paradigm for understanding nature and the universe. Okay. Quantitatively, look at that. Comp was so wrong. We've got numbers with 2 decimal places in them for the numbers of material, various elements in the sun. So, we have quantitative evidence here that spectroscopy is really probing what we believe to be the nature of the universe. The relevance today is, and again, I'm just going to skip through here. So what I've done so far is just tell you about the size of atoms, how they interact with the plasma, roughly. And here are some emergent spectra that we will talk about later. And now this is in the area. This is a higher resolution thing, and so you can see a few more Lyman lines in there. But here are what we usually observe with AIA, which we're all very familiar with if you're a solar physicist. Those little blocks of things. I don't know what ESP is. It doesn't matter. AIA is observing these things, and those are known to be formed because it's the UV. Remember, the photoelectric effect that Einstein discovered said you had to have a photon of a certain energy before you can knock electrons off. That's basically what he did. And conversely, what that means is that if you have a spectrum which has a lot of energy in it, then you see the emission lines like this. That can't be coming from deep inside the sun. There's no way, because by virtue of the fact that we're knocking electrons off here, those high energy photons have a very short path length. And so you just can't see deep enough into the sun at these kind of wavelengths. And so now we're looking way out in the sun, and we're looking at the corona. The sun is black in the absence of these lines. The photosphere is just radiating essentially nothing at these wavelengths. And even if it did, it would get absorbed on the spot and we wouldn't see it because of the photoelectric effect. Okay. So here is some blowups. Many people have worked with iris. Here is the short wavelength part of the spectrum. And so, for many of you, what I'm saying is very, very elementary, but that's the point here. I want to come at it from a basic physics point of view, not an observational point of view like this. The observations I'm showing just to indicate to you the kind of things that you can apply the understanding to. So pretty soon I'm going to be talking about these things here, the absorption versus the emission lines, and I'm going to switch briefly. We have 20 minutes left, so I think I'll switch to my other PowerPoint. And we will go to this one. So, oops, I need to change the sharing options. So let's share. So now, we've got past the first lecture, or the first material I put together for Fudan University many years ago. And now I'm going to skip the spectroscopy of modern solar physics because this was given to atomic physicists, right? So now we're going to look at isolated atoms and their radiation. So this is now getting into the guts of this thing. The focus will be on understanding simple atoms like hydrogen-like atoms, ions. So that means singly ionized helium, 9 times ionized neon, for instance, or they're exactly the same, except as I showed you, the radius of these atoms drops with charge as 1 over Z, the charge on the core, on the nucleus. So neon 10 is going to have little Bohr radii reduced by a factor of 10 compared with the hydrogen itself. That's really important to understand, and it comes from the Schrödinger equation, which we'll show in a minute. So the reason that's interesting is that a whole host of quantities based in Chianti, some of you will have heard of Chianti, the opacity project, the iron project, you name it, all these things have natural scalings which depend on the charge on the ion you're looking at. They also depend on the quantum number, like the larger the quantum number, the bigger the atom, okay? The small atoms, if you've got a thing with a radius of 1/10 of the radius of a hydrogen atom, say neon with 9 electrons removed, that thing then has a cross section sitting there in the embedded plasma 100 times smaller, Z squared. Okay. The energy also goes as Z squared. So if you plot Lyman alpha of hydrogen, that's at 1215 angstrom. For helium, Z is 2 instead of Z equals 1. That means it's Z squared higher energy. So that means 4 times more energy, or a quarter of the wavelength. 1215, 304. Now we go down to neon 10, it's a 100th of the energy. So it's around 12 angstrom. So these things can be understood very simply in terms of hydrogenic kind of spectra. The nice thing about hydrogen is it's analytical because you have a two-body problem. Analytical to the extent that the plasma is only a small perturbation on it. So the simple atoms can guide us and show us the principles without getting into the details of things like Chianti. The whole Chianti database things, what you will find is, if you take a random atom and say, look at hydrogen 1 and neon 10, then you will find the cross sections and the rate coefficients for collisions dropping exactly like this. It's that simple, right? And the reason for that is it's a two-level problem. We have analytical results. When you have an impact with an electron, that's no longer a two-level problem. You've got 3 particles. So even though hydrogen isolated by itself is a two-level problem, when you have electrons moving in, I'm just arguing that because it's a small perturbation, the cross sections will scale with Z like this. Think about now what Tom was saying about the Balmer series, n equals 30 in the Balmer series, right? That with L equals 28 has a lot of wiggles in it in the function, but it's spread out and its mean radius is enormous. It goes as n or n squared, I can't remember. We'll get to that. So again, you can see that if you look at things in the infrared, those tend to have very, very large cross sections because the energy differences are very small and the collision rates are going to be very big if they lie between high n levels. The low n ones tend to be, and they tend towards something called LTE, which is simply saying collisions dominate. And so the atoms have no choice but to be coupled to the Boltzmann distribution. And the only thing it can do is radiate with a Planck function radiation. On the other hand, for very small atoms which don't interact very much, like hydrogen, like magnesium 2, like calcium 2, there's not enough collisions to maintain that the atom is in a balance with the plasma, and the emergence of emission photons sort of drops the amount of support for it to be in equilibrium. So we'll get into that very quickly. And I'll often appeal to results from classical mechanics, like I just did, to help understand complex atomic systems. Just to confirm to you, here is a list of atomic radii. Well, this doesn't really mean much because what is the radius of an atom? I mean, it's a distribution, right, of charge and all that stuff. But you can see they're on the order of 1 angstrom, right? No matter what, even all the way to Mercury there. 1 to 2 angstrom. Okay, that's good to know. And now we know actually if we had, and you can see some of the, in the left-hand side, you've got lithium plus all the way to carbon, whatever it is. These atoms are shrinking, the radii are shrinking, according to, and it's not exactly according to Z squared because this is a multi-electron atom, right? So you can see that as a function of charge, and then you have negative charges, which I won't talk about here because that's a slightly different kind of, it's the same problem, it's just it's got different asymptotic behavior and what have you. Okay, we know that QM is about as good as we can do. Things like QED, the most accurate theory we have, and there's the, so, and I'm gonna finish in a minute or so. Again, I'm going slowly for you guys. I hope it's appropriate. So we're going to talk in the next couple of meetings about aspects of dynamics of these atoms inside plasma. And of course, that's going to involve perturbations of a thing called the Schrödinger equation, which is in a general case has to be itself a perturbative approach or some kind of optimization approach, because you've got a many-body system. I mean, helium has 3 particles in it, but no closed form solutions. And of course, helium, you go all the way to iron, you've got 26 electrons around it, and you've got a partially filled shell of d electrons and what have you. And it's a mess. It gets really complicated. But it's the principles that I want to bring out so that you don't get frightened of looking at some of these things. So we're going to talk about hydrogen and hydrogen-like. We're going to talk about radiative transitions. These are basically just saying when you have dynamics of electrons sitting around an atom, there are various ways in which the photons can interact with the pool of photons that we have to keep track of can interact with the plasma itself. And even if the plasma is controlled by, say, Maxwellian distributions, generally speaking, the photons don't interact very much in the outer layers of a star. Their mean free paths are very large, which tells you immediately that these things are loosely connected to the atoms. And this is the whole business of what's called non-alterative transfer. That's a posh word for saying that we have to self-consistently solve for a plasma that might well itself be Maxwellian, but the internal degrees of freedom in the atoms that you're trying to keep track of and make those emission lines and absorption lines that we're looking at, those things, we can't expect those to be in a thermal equilibrium state. And so we have to solve for imbalances. Equilibrium is all about something going this way being cancelled out by the opposite process, photonization versus recombination, collisional excitation versus collisional de-excitation. These are all processes which, if they were in balance, would lead to the internal degrees of freedom of the atom and its radiation to be thermal equilibrium. But this point is that it's a loose connection between the pool of photons and the plasma that causes us a lot of the really interesting things, like, for instance, the planetary nebula, why that's an emission line and not just simply a Planck function or something like this. So let's just have a quick look as to see where we're going. There's hydrogen. This will be next week. We'll be looking at the nature of these things, the wave functions themselves. See, there's a Z in those. So if you increase the charge, you end up with distributions, the exponential distributions of these things going as Z over A0. So the characteristic length is A over Z or Z. And so you end up with all those scalings I was talking about. We'll talk about dependencies on the wave functions on these principal quantum numbers, on the angular momentum quantum numbers, etc., etc. And we'll talk about the equivalence of a bound state, a very sharply bound state. That's the n equals 3 level, Balmer alpha upper level of hydrogen there. And there's the n equals 30 level and what that wave function looks like. And notice how we have this equivalence principle going from really quantum states at the top. They're all quantum states, but gradually, as you get bigger and higher quantum numbers, you get approach something called a plane wave, which is a phenomenon which is the wave function of a free electron. So one's going from very small states to almost bound, slightly bound states at n equals 30. That's a big old atom of hydrogen. Electrons are a long way out to one where there's a plane wave and just an electron going past a proton. So that's an equivalence between quantum and classical mechanics, which is a very sort of natural thing. And if you read Feynman's lectures and stuff like this, you'll understand why this thing is hard and solid, whereas it's actually mostly empty. And there's a bunch of atoms in there instead, surrounded by space. So I think I'll call it quits there. That's 50 minutes. That's more than long enough. We started at 5 past. And I want to thank you for listening and ask if anybody wants to discuss anything for a few minutes.
Yeah, Phil, I'm surprised, given that on computers we can simulate entire pieces of the sun. Why is it we can't find out the cross section for iron?
Well, we can, and the nature of the problem is to define the wave function of a multi-electron system and its evolution with time. And so the nuances, it depends on the question you're asking. I mean, I can tell you that iron 2, right, is and iron 1, they're the dominant spectrum in the sun.
That's
right?
why
I mean,
I asked.
Yeah. So, and the reason for that is that they have incomplete shells of electrons, which means that you end up with, and each shell consists of a bunch of hydrogenic-like wave functions. They have a principal quantum number, they have an angular momentum orbital quantum number, and those things, when you have such a small charge at the middle, you've got an equal effect of the interacting electrons with a skipping electron on the outside. So you jump from one wavelength to another and you see a line at 6302, which is what the advanced study polarimeter in Hinode observes. This transition is occurring in the presence of all these other electrons, which may or may not be frozen during the dynamics of that. They may join in the dynamics because it's a multi-problem. But also this thing has to be, in order to get cross sections for, say, the photon interaction between this level and that one, so that you can interpret where the line is formed in the sun, you have to have a very accurate description of the entire wave function of this thing, of this state going from one to another. It's not just an outer electron problem necessarily. If it is, you're in luck, because then you've got a dipole approximation that you can use for these jumps. But the thing is that these shells, when they're incomplete, you can very easily say have a 3D electron on the outermost part replaced by a 4s electron. The sun is going to generate a lot of those. And you can also have a 3D electron and you can have a 4p. These are all accessible to the kind of energies that are present in the sun. And so you end up with this enormously complicated spectrum. But the question you asked is, what is the numerical cross-section? And for that, you've got to have the total wave function of the atom, an operator, and the final total wave function of the atom. And then you compute this thing, and this gives you the probability, which is a cross-section, or by all other definitions, of a transition taking place. So you've got to get this very accurately. And when you've got such a complicated atomic model, you have things like correlations between different orbitals. In other words, the dynamics are coupled, and it's not clear that you can calculate positions of certain resonances that occur between coupled electrons. So you have a very, that's why things like, they do projects like the opacity project, and Iron Project, and why you have compilations of measured atomic cross sections as opposed to computed ones.
Yeah, my question is, why is it so hard to compute? Given the compute power we have today. which
Yes,
is
well, it's
immense.
probably not hard, but one of the things that you have to maintain is completeness of the wave functions.
Mhm.
And that can only, in principle, you've got an infinite number of potential states in an atom like that. Even for hydrogen, you've got an infinite number, but there you get a two-body problem, or an n-body problem. And so what this means is you're never sure if by going to including the possibilities of, say, instead of a 3D electron, a 5F electron, or adding in an 11D orbital, if that's going to affect. And the only thing you can do is increase your basis for expanding this thing and then look at where
The convergence.
the convergence. And you can never prove convergence, right? All you can do is look for a lack of change between one and the next. But around the corner, there might be another thing going on. Now, you can make physical arguments as to why that might be the case. But that's why it's different. I mean, and I would say that, yes, while we make what we call simulations of the sun, I'm very puzzled as to why we want to simulate. I don't know what the point is of actually simulating something as opposed to doing a numerical experiment. Because the information content that comes out of a simulation in the radiation, that's all we can observe, is very convoluted. And there's a lot of redundancy in that information, the spectrum coming out. And so I would steer clear of doing what I call simulations, where the point is to compare something with the sun, an event on the sun, and basically using numerical calculations to understand plasma dynamics instead. But that's just my opinion, and it's not shared by many people.
Thank you.
Anyone online want to, or are we all ready for coffee now? I think I'm about to fall asleep. All right, so thanks so much. 11 o'clock. Thanks for joining. Please do let me know as to the appropriateness and level of detail, and what you want to hear further, and if there are things. And also, if there is something, I think I would like to invite anybody who wants to has a question to just maybe prepare a slide and share it during a meeting or two, just to cement some ideas and help people puzzle things out, like where have all the Lyman lines gone, that kind of thing.
So it sounds like a possible hit song by Simon and Garfunkel.
Where did all the Lyman lines go? All right, thanks everybody. All right.
Thanks, Phil.
Thank you.